Hello again. We will continue talking about Fourier analysis in one way or another. You know, it's a periodic subject, periodic transforms. Everything's periodic. We'll just go on forever, it seems. But today we'll give a little bit of an optional lecture. It's not essential, but it's important practically, and it's very interesting. And it's very interesting not just that you have to learn the technical details, but you should understand that there really is an art to measurement, and the consequences of doing a measurement and in understanding it mathematically are often quite subtle in a very fascinating way. So let's go on and talk about that. Okay. So we'll talk about aliasing. We'll describe what aliasing is. We'll describe some of the consequences of aliasing. Then we'll give a few ideas of how you can eliminate aliasing, and then we'll give you some homework to do, an assessment. What else could you be? So let's play God for a moment and say someone else is doing a measurement, and we know that what they're measuring contains two functions. Okay? They don't know that yet. They're just sitting there in their lab, slaving away with their little meter or something, measuring as if it was a meter stick, but they're really measuring electronically by reading dials or having it fed into a computer. But they're trying to measure a function. Fine. But we know that what we've put in is actually two functions, a sine pi of t over 2 plus a sine of 2 pi over t. Either plus or there's two functions being set into their counter, and they're trying to distinguish between the two of them. So that's the issue here. How do you distinguish between the two of them if you don't know there's two there? And how do you see the consequences of these two interfering? Maybe they don't interfere. How do you know what happens? That's the issue. Okay? If all you do is do measurements, you're limited. Okay? So you could, for example, be a very unlucky graduate student or grad student or undergraduate student, say, let's say I do all my measurements at time t equals 0, 2, 4, 6, 8, etc. Well, those corresponds to the points 0, 2, 4, 6, 8. Not only can you not discern the difference between the dashed and the solid function, you don't see anything. All you're measuring is zeros. So you would tell your professor, hey, prof, there's no function there. You gave me no data. I measured it 1,000,000 times. There had to be something there. Well, okay, he could find a new student, or you could go on and say, well, no, I can be a little better than that. I just measured uniform steps. If there's something there, maybe I have to look at non-uniform steps. So you'd say, okay, let's try 0, 12/10, which of course is 6/5, 4/3, etc. You have a whole series here. So I've done another infinite number, and they're not uniform. So now I have values like this, here, so forth. Ooh, and what's happening, of course, is both functions are equal at that point. So I get a signal, lo and behold, but which signal, if I do a DFT, will be reproduced? Well, the answer is, of course, neither. Okay? Basically, most of the high-frequency components you're missing, so you won't. They'll sort of fall between the cracks, but sort of. Some of them you'll pick up if you do a usual DFT, and they'll contaminate your low frequency. So you don't get either of them right. So let's see an effect of that. And you've probably seen an effect of that already. So these are our two functions, and it's known as Fourier distortion. So here's a photograph of a brick wall. And what about photographs? Well, photographs are recorded digitally. Essentially, a Fourier transform or now a wavelet transform. And we'll talk about wavelets at some point shortly. And then only so many of them, of the transforms, are kept. So here, if you do a Fourier transform and you don't keep all the high-frequency components, some of them leak into the low frequency, and they give you this ripple effect, or this Fourier pattern effect. And that's aliasing. That's a consequence of aliasing. And you wouldn't like that, if it was your wedding picture or something, so you'd have to get rid of that. So in common colloquial language of science, we'll say that the high-frequency components can contaminate the low-frequency components. It causes Fourier distortion in the synthesis. And then in a little more complicated way, it's often said that the high omega is aliased by the low omega. So the low omega picks up some of this high-frequency component that's there. Okay? How do you get rid of it? Well, the good thing about all of this DFT business is it's just sines and cosines. It's not really rocket science where you have to do some complicated algebra and calculus. It's just sines and cosines. It's all trigonometry. So you can just look and measure and count the number of steps, the number of frequencies. So we'll start off by saying let's define a sampling rate S. S for sampling. And it's just the total number of measurements, capital N, divided by the total time, T. Okay? So that's the sampling rate. It's used all the time. And then we have the question. When will one frequency, omega, and another frequency, omega minus 2f, have exactly the same DFT? Of course, you'd never ask a question like that. It really goes the other way. You say, if I measured S, what's the consequences on it? And you find out that, oh, omega and omega minus 2s have the same DFT if the sampling rate is less than omega over 2, or equal to omega over 2. So, you know, that had to be someone who was either smart or very patient. Mr. Nyquist figured that guy out. Okay? So that's known as the Nyquist criteria. So, how do you eliminate aliasing? Well, you eliminate aliasing by doing better and more measurements, of course. Okay? So we have our sampling rate, S, the same, hasn't changed from the last slide. And if we have a signal which had no frequency greater than S over 2 in it, then there wouldn't be any contamination. You know, the low frequency couldn't get aliased by the high frequency, and we wouldn't have any of this Fourier distortion. So you say, fine, how do you do that unless you play God? Well, you can't play God maybe all the time, but you can do something like that. You can say, let me take the frequency I actually measured in the laboratory and filter out the high frequencies. I'm not going to measure them anyway. I'm not going to put them in my Fourier transform because I don't have enough measurements to do a good job on the high frequency. So let's just get rid of the high frequency so they don't measure up the low frequency, which I try to do a good job at. Fine, that's good. And we'll talk about one way of doing that known as a sinc filter in electron filtering. If not, you know, you have at your disposal many filters. That's one that could do it. So we said all that. Okay, so what we need to do both is do a higher frequency, higher sampling rate to do a better job. If not, get rid of the highest with this sinc filtering. And if you want a good spectrum in the middle, recall our spectrum repeats. So anything near the end is highly suspect. So you want it to be good in the middle, and you get that by having a higher sampling rate. So, and padding, we talked about previously, padding will give you a smoother y of omega, but it won't solve this problem. That's adding zeros to the end. So that's it. Now it's time for you to go home, do your homework, try to do some assessment. Okay? So take our function here. Say you have a sine of pi t over 2 and a sine of 2 pi over t as your input. Assume those are your measurements and do a DFT on them. You know that the real answer should have two peaks, in this case of equal value, one at pi over 2 and the other at 2 pi. See what happens. See if you get those and see if you get the right amplitudes. And do this for various sampling rates. Start with a low sampling rate. As with any algorithm, you always want to see where it fails. Then you know what it looks like when it fails. You know what failure looks like. And then you should know what success looks like when you don't have anything that looks like a failure. That's not hard. Okay? So look at low sampling rates, see it fail, and then verify that the problems go away as you increase the sampling rate. So that's verifying the Nyquist criteria computationally. For those of you who have a little more ambition, try using some kind of a filter or read ahead in the book and do that. Filter out the high frequency and see if that works. But enough for now. That's optional. Hope you enjoyed it. And we'll get on now. We'll talk next probably about fast Fourier transforms. But don't think about that. Go to the lab, do your homework. Bye for now.